interval. So 21 through 41 were really good problems to consider. And a word of caution with problems like that, you take the derivative, set the derivative equal to 0, solve for x. Well, sometimes you get solutions there that are outside the particular interval. Like it says between 2 and 5, and the derivative is equal to 0 over -7. You don't care about that. So you don't evaluate the function -7. It's only a critical number if it's in that interval. So sometimes that happens. You have to be on the lookout for those. Probably one like that on the test. Locate the absolute extrema of the function on these not necessarily closed intervals. In fact, for 43 and 44, we're guaranteed that they exist because these functions, I believe, are continuous on these closed intervals. But if we lose an endpoint, then it might be that we lose a maximum, or we lose a minimum, or maybe we lose both. So 43, I think 43 is just from its simplicity. It's a piece of a line. It's a piece of a line segment. So the line segment, which may or may not contain both of its endpoints. So if we lose one of the endpoints, do we lose the maximum? Do we lose the minimum, or does it have one of each? So that's a pretty good question, I think, to think of. I might also indicate 44, except that it doesn't have the answers. So 43. Other good ones to look at. Wow, let's not do those. What about these? Let's not do those either. Or these. Or those. What about these pictures? Determine from the graph whether f has a minimum in the open interval AB. Could we do a problem like 68 if we had to? Problem like 68. 68, this one right here. Look at the graph. Here is the A function there. On the open interval from A to B, it looks like it's not defined at either one of the endpoints, and also at this point in the interior of the interval where it looks like there's a cusp, where it looks like it dips down there to the little open circle there. Does the function, let me see, make sure I get the question right, does the function f have a minimum value in the open interval AB? What it has is a greatest lower bound. Whatever the y-coordinate of that open circle is the greatest lower bound. Any number below that would also be a lower bound, a number lower or less than any value of the function on that interval. And the number, the y-coordinate of that point, is less than any value of the function on that interval, but it's not a value of the function on the, and it's the two things. It's greater than any other value that's less than the value of any value of the function on that interval, but it's not a value of the function on the interval. If we go above that, pick any number greater than that number, there will be something less than that. So there's not a number that you can say is the minimum value of the function on the interval. Just there is a greatest number that's less than the value any value of the function on the interval. So the answer is no for that. The answer is yes for the next one because it's a solid dot. The y-coordinate of that point is the minimum value of the function on the interval. So that makes the difference there. What about, I could suggest 67 and 69 as problems for you to think about. But let's look at this problem 69 right there. Open circle there, solid dot up above it. Does that function have a minimum value on the interval? The answer again is no. The y-coordinate of that point is the greatest lower bound, but it is not the minimum value of the function because the function doesn't take on that value. The B part. Does the function have a minimum value on the interval? It does. The solid dot in this case is below, so the y-coordinate of that point is a value of the function on the interval, and it's also less than or equal to any other value of the function on that interval, so it is the minimum value of the function on that interval. So good ones to look at. Let's mention 67 and problem 69. as well. And I think that's probably enough from section 4.1, but I might be wrong. Some of these look good. Not that one, not that one. Nope, let's keep going. 4.2, Rolle's theorem. Typical problem in this section is this. You want to make sure that you know the specific hypotheses that are stated for Rolle's theorem and the specific hypotheses that are stated for the mean value theorem. For Rolle's theorem, the function has to be differentiable on the open interval, AB. It has to be continuous on the closed interval, AB. And f of A has to equal f of B. If it is, and the picture might look something like 4.2, the picture might look something like this. There's f of A, the y coordinates there. The conclusion is that because it has to go through that point, and it has to go through that point, and it has to be smooth and continuous in between, there has to be some point in between. It does not give us a way to determine where that is, but it has to be at least one number c in between where f prime of c equals 0, and when f prime of c equals 0, that results in a horizontal tangent line. Yes?
Does it have to be symmetrical on the c line there?
Does c have to be halfway in between? Is that what you're saying?
Yeah.
It does not. In fact, there could be multiple values of c. C could be on the far right, far left, as close to a or b as you please when you design a function to do like this. Or there could be, you could rig up a wild and crazy trigonometric function that would go up and down like that and intersect, how to say this, have just as many horizontal tangent lines in between there as you like. Or, if the function's constant on the interval, every single point on the interval would be a place where f prime of c equals 0. The mean value theorem, so that's Rolle's theorem. The mean value theorem is slanted. Ooh. It is slanted, but let's draw the x-axis, and then curve, something like that. And there's A, f of A, and there's B, f of B, and there is a secant line, straight line connecting those 2 points on the graph. Oh, goodness. 2 points on the graph of that function. So one hypothesis we do not need from Rolle's theorem. For Rolle's theorem, it has to be that f of A equals f of B. Erase that. We don't need that for the mean value theorem. For the mean value theorem, we have the other two, though. It does have to be differentiable on the open interval from A to B and continuous on the closed interval from A to B. So it's got to connect with the endpoints as they're drawn there, and it's got to be smooth in between. So if both those things take place, there exists a C in between. Don't know how to find it, but we can show that it exists such that the slope of the tangent line, to the graph at that point is the same as the slope of that secant line. And it turns out to be surprisingly useful in proofs of theorems that we look at for increasing and decreasing, as well as some that we'll look at when we look at integral calculus, mean value theorem. So as far as the test question goes, here's a function, here's an interval in the domain of the function. Show that the function satisfies the hypotheses of either Rolle's theorem or mean value theorem. And to show that it's continuous, basically if it's a polynomial, say it's a polynomial. Therefore it's continuous on the open interval and it's sorry, differentiable on the open interval, continuous on the closed interval. And if it's Rolle's theorem, just verify that f of a equals f of b. If it's a mean value theorem, you don't even have to do that. For the mean value theorem, you calculate f of b minus f of a over b minus a. And what the problem on the test basically will say, find values of c in the interval whose existence are guaranteed by the mean value theorem, for example. So you find the derivative, set it equal to this expression, solve for c like we did in class, and find values of c. So it shouldn't be a very difficult problem, but it makes you, well, memorize the mean value theorem, what it says, and actually see the thing in action. I think that's about as exciting as the problems get in that section. So, problem 9 and actually 11 through 22, probably most of those are good ones there. Not thrilled that it does that. What can I do? I can do that. I can do that. And then back like that. There, okay. So, 9. And what else? 11 through 21, odd. Are there any ones there that I really don't care for? Oh, I think there's some good good food for thought there. So 11 definitely is good. 13 is typical. 15, a potential issue with 15 could be that it might have a point of non-differentiability at 0 maybe. And you might say that Rolle's theorem cannot be applied because there's a point of non-differentiability at 0. It has to be differentiable on the open interval from -8 to 8. 16, same thing. You take the absolute value function and you shift it 3 units to the right and reflect it about the x-axis, and then you shift it 3 units up, and you got something that looks like this, and that tip is going to happen at x equals 3, and that happens between 0 and 6. So that one's also going to have a point of non-differentiability in that interval, and when that happens, we cannot apply Rolle's theorem. So you can say Rolle's theorem does not apply to that. 17, does it have a vertical asymptote between -1 and 3? I don't know. -2 is not between -1 and 3, is it? No. It seems like it should be okay then. That rational function doesn't have a vertical asymptote. I can't think of another situation where there would be a point of non-differentiability. It's going to be continuous. It's going to be differentiable everywhere in its domain. So 17 seems like it would be okay. 18, there will be a vertical asymptote at 0. That's between -1 and 1. So Rolle's theorem will not apply. 19, a product of 2 differentiable functions. So that should be fine. It's just a matter of finding the derivative using the product rule, set it equal to 0, and finding what you need there. 21 should be very straightforward. So 15, 17, 19, 21. And similar sorts of problems, except, oh, graphing utility. Similar sorts of problems. Why am I not in love with problem 23? I'm just not. (35) and 36 are nice. They just don't look like the types of problems I would put on a test. 37 and 38. 39 and 40. Explain why the mean value theorem does not apply. Why does the mean value theorem not apply on the interval from 0 to 6 in problem number 37?
It's not continuous.
Yeah, there's because that point's above the graph, it's a discontinuity, and it has to be continuous on the closed interval from 0 to 6. Why not for 38? We got that sharp, corner. I guess it's somewhere between a corner and a cusp, and it's a point of non-differentiability at 2. It has to be differentiable on the open interval from 0 to 6, and that one's not differentiable there, according to the picture. So that's why the mean value theorem does not apply. Why not 39? What's going on there?
Non-continuous.
The discontinuity of vertical asymptote actually at x equals 3. That's between 0 and 6. So we cannot apply it to that one. And 40?
Non-differentiable.
A point of non-differentiability at 3. The translation of the absolute value, there's a corner in the graph. So at x equals 3, it's not differentiable. What else, what else, what else? Here we go. Problem on the test is likely to look like one between 43 and 55. So 43 is 43 is a nice one, maybe a little too nice. Oh, I really shouldn't rule out these others, should I? We kind of did them, but it doesn't mean they're bad. 37 and 39. So 21, 37, 39, 43, 45 is a good one. 47 is weird. What's weird about 47? 47 could work. If there's a point of non-differentiability, it seems like it would happen at 0, but 0 is one of the endpoints. So that should be fine, right? It should be differentiable on the open interval from 0 to 1. It's also continuous on the closed interval, although it's not differentiable at 0 itself. It's certainly continuous from the right at 0. So I'm thinking it applies to 47. 49 has a point of non-differentiability at -1/2. 51 is just not very interesting.
Mr. Rizzo?
Yes.
Are we going to have any questions? Is there a possibility that we'll have any questions where it can't apply and we have to write that down then?
I think probably we ought to at least allow for that possibility. So it'd be great if I phrased the question a lot like this. Maybe give you a couple, one where it applies, one where it doesn't. Let's include 49, 51, even though it's not very interesting. 53, the function's going to be decreasing throughout that interval. Wow. (53). What do they want you to do for that? E to the -3x on the interval from 0 to 2? Before I give you that one, let's see if it's something I might want to grade. F prime of x is derivative of e to a power is e to that power times the derivative of that power. So it's going to be -3 e to the -3x. So copy and paste the e to the -3x and then multiply by the derivative of the expression in the exponent. In this case, since it's just linear, it's -3. So that's f prime of x. So we need to consider f of 2 minus f of 0 over 2 minus 0. Well, we should if it satisfies the hypotheses, but it does. It's the exponential function, just composed with -3x. The composition of continuous functions is continuous. No reason to believe this should not be differentiable everywhere. So it's it's going to be nice and smooth from negative infinity to infinity, in particular between 0 and 2. So what's this going to look like? This is going to be e to the negative 6x minus e to the 0 over 2. No, e to the negative 6. E to the negative 6 minus e to the 0 over 2. So that's the slope, and we're saying there's a number in between 0 and 2 where the slope of the tangent line is actually equal to that value. So what is the slope of the tangent line? Well, f prime of c would be negative 3e to the negative 3c. So if we say f prime of c equals e to the negative 6 minus e to the 0 over 2, then negative 3e to the negative 3c equals e to the negative 6 minus 1 over 2. Solve this equation for c. Is there a nice algebraic solution to this, or would we need to do a graphical approximation? We could isolate the e to the negative 3c, and we could take the natural log of both sides. We could do it with a regular calculator. Doesn't look like it's going to be pretty, though. E to the negative 3c equals e to the negative 6 minus 1 over negative 6. Divide both sides by negative 3, and take the natural log of both sides. Now let's think, the number on the right-hand side is positive, isn't it? Because e to the negative 6 is way less than what? Well, it's between 0 and 1. But it's tiny number, close to 0. So to subtract 1, we get something negative. Divide by negative 6, we get something positive. So because it's positive, it makes sense to take the natural log of both sides. So negative 3c would equal the natural log of e to the negative 6 minus 1 over negative 6. So c equals negative 1/3 times the natural log of e to the negative 6 minus 1 all over negative 6. That's the value of c whose existence is guaranteed by the mean value theorem. I would suggest someone take a look and see. You might crunch it out on a calculator. I'm not going to put that one on the test. 53 does not look like a good one to me. So 51 appears to be good. 50, well, that seems plenty. Yeah, that looks like plenty from section 4.2. Next, 4.3.
Yeah, 53 just leaves it as derivative of f to the ln cube root of 6 over 1 minus e to the negative 6 equals e to the negative 6 minus 1 over 2. That's all it says.
Wow. Yeah, I would want to have a look at that and see what it wants with that. 4.3. Okay, we've just begun this section. Well, we've begun it, but we haven't finished it. So it might be good to go ahead and finish it and then talk about props. So let's do that, and I'll come back and indicate these. We talked about what it means for a function to be increasing. We said that mean value theorem can be used to prove that if a function is that a sufficient condition for a function to be increasing on an interval is that f prime be positive on that interval and it be continuous on that closed interval. Similarly, if it's continuous on a closed interval and f prime is negative on the interior of the interval, then it's decreasing on the closed interval. And if function is continuous on the closed interval, and f prime is equal to 0 for every value of x in the interior of that interval, then f is constant on that interval. We talked about critical numbers for a function. We look for critical numbers on an interval, basically in the interior of the interval, and they happen one of two places, where f prime is equal to 0 and where f prime is undefined. This is where a function may have a relative minimum or relative maximum. If it happens in the interior of an interval, then, well, let me get the theorem. If f is, hang on. Sorry. We've not yet done the first derivative test. But we did example 1, is that correct? We did example 1 to indicate where it's increasing and where it is decreasing. It was just about to take us back over some paths we covered in section 4.2. Didn't want to do that. Let's pick up with the first derivative test here in section 4.3. Suppose f is continuous at a critical point x sub 0. We've also called these critical numbers. Critical values also would work. And we have this additional information about the sign of the first derivative on intervals extending, open intervals extending both to the left and to the right. So imagine a point on the graph, and we know that to the left of this, I'm going to construct a little sine graph for f prime. Sine graph for f prime. On an open interval extending left from x sub 0, f prime is positive. So pluses right here. F prime is positive on that interval. And on an interval extending right from x sub 0, f prime is negative. So to the right, it's negative. Here is x sub 0, and that is a critical point, meaning that either f prime is undefined or f prime is equal to 0 right there. Maybe we have a horizontal tangent line. The pictures I may draw may imply that f prime is equal to 0, but it could be a point of non-differentiability. If f prime is positive, does that mean the function's increasing, decreasing, or what? Increasing. If f prime is positive, it's increasing, so the graph is looking like that. It increases up to that point. On the other side of that, if f prime is negative, then it's decreasing away from that point. And so, the conclusion is that f has a relative maximum at x sub 0. That seemed to make sense as far as the picture goes. Now, we'd like to be able to apply the first derivative test even if we don't have the picture in front of us. We just know that it's continuous at that critical point, and derivatives positive to the left, negative to the right, then we can see at this point at the top of a hill. Another sine graph, there's x sub 0. If f prime is negative to the left, but positive to the right, well, negative to the left would mean that it's decreasing coming into the point. F prime being positive to the right would mean that it's increasing going away from the point. So what's the conclusion? F has a relative minimum at x sub 0. So decreasing into it, negative derivative, increasing out of it, positive derivative. So it's a point at the bottom of a valley. And let's see. Two pictures for the last one. Here's x sub 0. If f prime has the same sign, say f prime is positive on both sides. Positive, 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 positive. Let's see how such a thing could happen. Even if it's a horizontal tangent line, this could happen, say, for example, with y equals x cubed. Y equals x cubed, it's increasing, it's increasing, it's increasing, it's increasing, kind of levels off, and then continues to increase. So the slope of the tangent line goes to 0, but it never actually begins to decrease. And it's only at only 0 at that one point. So if the picture's like this, and then that, it's increasing going to it, it's increasing coming out of it, there's no relative minimum, because look at any open interval, and I'm just going to draw this on the graph, but we think of it as being an open interval like that. There are going to be points above that value and below that value. Well, no minimum because they're points above, and no maximum because they're points below. So, neither. And suppose it's negative going in and negative going out, like this and like that. Not at the top of a hill, not at the bottom of a valley. So, neither a minimum or a maximum. So in a case like this, you might not know the function, you just have some information about the sign of the first derivative to the left or to the right, and you want to be able to conclude if it has a relative minimum, relative maximum, or neither. This is the first derivative test. And first modifies derivative, it's a test for relative extrema, which involves the first derivative. Section 4.4, we'll see a test for relative extrema, which involves the second derivative. Example 2. Analyze the relative extrema of this function. Well, I've got this piecewise function, which basically does everything we want it to do for the various scenarios. Let's see if we can differentiate it piecewise. So we have an idea of an expression which would define the derivative on the interval from negative infinity to 1, and an expression which would define the derivative on an interval from 1 to positive infinity. And because just by inspecting the graph, I think we'll be able to tell that there's a point of non-differentiability at x equals 1. So we're looking for zeros of the first derivative, and we're looking for places where the first derivative is undefined. So let's take this expression, d dx of x plus 4 times x plus 1 quantity squared. Let's differentiate it. And then at least on this portion of the graph, we will have an expression where if we substitute a number for x, it would give us the slope of the tangent line to the graph at any of those points. It won't be valid when x is greater than 1, but we can come up with a different expression for that one much more easily. So here goes. You think a product rule? That's one option. Or we could just multiply the whole thing out and use the power rule, but then we have to factor it back. I think we'll be able to salvage some of the factorability of this if we use the product rule. So it's going to be the first times the derivative of the second. So that becomes a 1, and then we multiply by the derivative of x plus 1 according to the chain rule, but that's 1, so it's not a big deal if you happen to forget to do it in this case. First times the derivative of the second plus the second times the derivative of the first. X plus 1 quantity squared times 1. Derivative of x plus 4 is 1. Now, kind of clean this up a little bit. This expression and this expression, two components of the entire derivative, each one of those has a factor of x plus 1. So my suggestion would be, as we're cleaning this up, rather than clearing parentheses, we take advantage of the fact that we see that common factor and we factor out the x plus 1. It'll just help us with the factoring on the back end here. So x plus 1, and then something like this. We look at the first component, this one right here, and we ask ourselves, what can we multiply x plus 1 by to get that? Two times that quantity x plus 4, that's what's missing. Then put a plus, and then ask ourselves, what can we multiply x plus 1 by to get this other component?
X plus 1.
X plus 1. That's bizarre. So I can make it go away just by Scratching on it? Whoa! A whole new functionality of Microsoft Journal. So if I say something stupid and I want to make it go away,
Maybe that should be a smaller scratch.
all right.
It'll probably turn the pen around though.
It was a nut. You think?
Yeah, that's how it usually works.
Yeah. That's why there's a big red eraser.
Handle.
No, you have learned.
Wow.
Try that one out.
So if I say something stupid, like the fact that I've been using this for over a year now and not known that, I can just erase it. Wow. That's beautiful. All right.
There's still a dot of it
Yeah.
by the Cartesian plane.
A dot? Where? I'll get it.
By the Cartesian plane on the bottom right.
This dot? A dot here?
Yes.
Got it. Wow. Oops, another one. You learn something new every day. Yes, thank you. X plus 1 times 2x plus 8 plus x plus 1. X plus 1 times 3x plus 9. Now maybe factor out the 3. 3 times x plus 1 times x plus 3. So as I'm trying to differentiate this thing piecewise, f prime of x equals 3 times x plus 1 times x plus 3. And I can do this on the open interval, the one that does not include the 1. What happens at 1? It's not to say it's differentiable there, but it is differentiable everywhere less than 1. And over here, what's the derivative? ddx of negative 2x plus 22. Negative 2. So negative 2 if x is greater than 1. Now a couple things without pulling out the limit definition of derivative. Let me just establish some sufficient conditions for the function to be differentiable at 1. Basically, we need two things. As x approaches 1 from the left and as x approaches 1 from the right, the two pieces of the graph need to be, how to say this, f prime, the limit of f prime as x approaches 1 from the left needs to equal the limit of f prime as x approaches 1 from the right. They need to be able they need to be approaching the same amount of steepness, so that when they fit together, they'll have the same slope, like that. It also needs to be continuous there. Now the continuity is fine, because if you evaluate the top expression at 1, you get whatever 5 times 2 squared is. I guess that's 20. And if you evaluate the bottom expression at 1, then that's going to be 20. So they're both approaching the point 120. So it is going to be continuous, but from the left, the slope there is approaching whatever 3 times 2 times 4 is. Is that 24? I believe so. So the slope of the tangent line here, m sub tan equals 24, and that's dramatically different from the slope of the tangent line here, m sub tan equals negative 2. That there's an abrupt change, a discontinuous change in the slope of the tangent line from 24 to negative 2, so it results in a point of non-differentiability. It's not smooth. It's not smooth. So we can look for critical numbers now that we have the first derivative. We have critical number at 1 because it's a point of non-differentiability, and then we look for where f prime is equal to 0, where it's not going to be 0 for values greater than 1 because it's always equal to negative 2. But for values less than 1, it might be 0, so I'm trying to find where f prime of x equals 0. I would want to figure out where 3 times x plus 1 times x plus 3 is equal to 0. Yes.
-1 and -3.
Yes. X equals -1 or x equals -3. They both qualify as critical numbers. So we have 3. Wait. No, it's okay. There's one more thing I need to say before I should have said they both qualify as critical numbers. I should have also said, and they're both less than 1. Because if one had happened at 2 or 3 or 4, it wouldn't have counted, because so we're only using this expression for x less than 1. But they're both less than 1, so it's good. The other one is 1 itself, because that's where f prime is undefined. F prime of x is undefined at x equals 1. So 3 critical numbers. What we want to do is apply the first derivative test at each of those critical numbers. All right, let's try it at x sub 0 equals -3. Now, what I think I want to do is a sine graph all the way from -infinity to +infinity, and if I have that complete sine graph, I'll be able to inspect the sine graph and tell what's going on with each of these critical numbers. It would seem a little bit unnecessary to do this one at a time. So let's construct a complete sine graph for f prime. I'll put those critical numbers on there in order from left to right: -3, -1, and +1, and choose a test number at each interval and evaluate the derivative at each interval. The derivative is only going to be able to change sign when either it's undefined or it's equal to 0. So it's not going to change sign within each of these intervals. So let's try -4, -2, 0, and 2 for our test numbers. F prime of -4. Well, I'll refer to the piecewise derivative that we have up here. If we substitute -4 for x, -4 plus 1 is -3. -4 plus 3 is -1. So -3 times -1 is +3. Times 3 is 9. So it looks like 9. So the slope of the tangent line there at -4 is 9. It looks like it could pass for 9. The point is that it's positive. Positive slope. How about -2? Substitute -2 there and there. And we get -2 plus 1 there is -1. -2 plus 3 is +1. So 3 times -1 times +1 is got to be -3. -3, does this look like a slope of -3, perhaps? So since f prime of -2 equals -3, we get minuses along there like that. How about f prime of 0? We still get to use this. 3 times 1 times 3, is that 9 again? Does it look like that line is parallel to that line? Maybe they both have a slope of 9, but it does look like f prime of 0 equals 9. So it's positive. And finally, f prime of 2. Now, if x is greater than 1, we're going to use this other expression, the -2. So f prime of 2 equals -2, and it is negative right there. Now we have the picture in front of us, but if we apply the first derivative test, kind of in the absence of this picture, we can say, okay, the first derivative is positive in an interval extending to the left, indicating it's increasing going into it, negative in an interval extending to the right of -3. So does it have a relative extremum there? It does. And the relative extremum, let's see. So analyze. So that's the conclusion. F has a relative maximum at x equals -3. That's one conclusion that we have, because it's positive to the left, f prime is, and f prime is negative to the right. How about at -1? It's negative to the left, yes.
Isn't that just a written version of visually checking to make sure it actually goes back down?
The pluses and minuses?
Mm-hmm.
Yes. The pluses and minuses, in the absence of the graph, if we have information about the function, but we don't have enough information to sketch a complete graph, then it's telling us this. So the minuses to the left of -1 tell us it's decreasing, going into the -1, and the pluses on the other side tell us it's increasing. So f, the first derivative test, has a relative minimum at x equals -1, and the pluses going into the 1 and the minuses going out, coupled with the fact that it is continuous there. It could get a little dicey if it's not actually continuous at that point, but it is. We've shown that. So f has a relative maximum at x equals +2. There we go. In each case, by the first derivative test. And the graph confirms it, of course. If y'all believe my graph.
Yeah, don't you mean 1?
I mean 1. And I meant, should have gone 1. I was referring back to this. This is where I initially, old habits are hard to break. F prime of 1. No. Yes.
It's undefined.
Is no. I was right the first time, but I was wrong the second time. F prime of 2 is negative, but I do mean at x equals 1, because 1 is the one we were testing it. Thanks. Yeah, that's right. Yeah, but 2 was my test number, so the test number was inside the interval. I evaluated it. It found a negative slope of -2 there. And so because it's positive going into x equals 1, it's negative coming out of x equals 1, has a relative maximum at x equals 1. Yeah. Sorry about that. Yes?
Weren't you taking your test numbers, in like the last one,
Mhm.
f prime of 2, you took the test number and you put it in the equation 3x plus 1, x plus 3? Is that right?
Actually, I put it right here. There was no place to put it because there's no... I just said because the 2 is greater than 1, then I look at this to tell me what f prime of 2 is. So it's just -2. And I got the -2 by taking the slope of this line.
So it doesn't matter what number we put up there.
So it would have been the same for 3 or 4 or 5. All throughout here, since the slope of this is -2, f prime is constant on that interval. But since it's negative rather than positive, we get a change in the first derivative test. Had it been 2x plus something, even if it had been continuous here and it looked like that, then what would have happened is that there would not have been a relative maximum there. If it had been positive going in and then still positive coming out of there, then we'd say it does not have a relative maximum at that point. That might have been a good example, but it worked out that way.
Is it safe to say by this point that 4.4 won't be on the test?
Yes, absolutely. 4.3 we'll finish in just a little while. And hopefully we'll start 4.4 today, but 4.4 will not be on this test, but the next one. Mm-hmm. Example 3. Okay, polynomial, and I've gone ahead and differentiated it, but it's not difficult, so maybe I should walk through it, because the derivative will not necessarily be provided on the test. So analyze the relative extrema. Well, we could look at the picture, of course. but the picture is there simply to substantiate what we're doing with the derivatives. Nice polynomial here. Analyze the relative extrema using the first derivative test. So this is going to be differentiable everywhere, so we won't get any critical points for points of non-differentiability, but there may be a couple points where the derivative is equal to 0, and we'll get critical points that way. So here goes, f prime of x equals 12, x cubed minus 84x squared plus 180x minus 108. We can factor out, I think, a 12. 12 times x cubed minus 7x squared plus 15x minus 9. Now, the third degree polynomial here was designed to have nice zeros. If the zeros aren't all that nice, we may have to content ourselves with decimal approximations for them. But since it is nice, when we appeal to the graph, we should be able to see what the x-intercepts are, so that a little bit of synthetic division will help us to find the other factors. So look at the graph. Really don't need the 12. I'm just concerned with the zeros of the x cubed. There's a 0 this one, it'll be a 0 if we tack on the 12. Minus 7x squared plus 15x minus 9. Zoom 6. By the factor theorem, zeros of this will point us to factors of the expression. And it would appear that 1 and 3 are x-intercepts. So just confirm that second calc value, x equals 1. Sure enough, 1 is a 0 of this expression, and 3 also is a 0. So we get a couple of factors, and I think I could even skip out on the synthetic division here, because again, looking at the graph, x minus 1 and x minus 3. But what can we say about the multiplicity of each of these zeros based on the graph of the polynomial? What do you think?
X minus 1 only has 1 because it crosses.
It crosses, so multiplicity 1.
X minus 3 has 2 because it touches.
It touches at x minus 3. So that has even multiplicity, and can't be more than a couple more for this function. The degree is only 3, so that one would have multiplicity 2. Now we could check and multiply this out and see, but it really doesn't have a lot of options other than this. This is pretty much the polynomial we're locked into. So this is f prime, and since this is f prime, we can set this equal to 0 and solve for x. By inspection, we can tell where the critical points, critical numbers will be. So x equals 1 and x equals 3 are possible locations of relative extrema. They may or may not occur at these. We'll see it. We do get a relative extremum at one of these. We do not get a relative extremum at the other. To see where we get relative extrema, we get construct a sine graph for f prime. F prime can only change sign at critical numbers. So if we put a 1 there and a 3 there and test numbers in each of these intervals, whatever sign we get for the derivative in each of these intervals is the sign of the derivative throughout that interval. So what is f prime of 0? I think the best place to go is the original and just say I want to say it's negative 108, just from the original, because the 0 kills the first 3 terms and just leaves us with a negative 108. We could say 12 times negative 1 times the square of negative 9, but that's also negative 108. So negative 108, so the derivative is negative. And just by inspecting the graph, the function's decreasing. throughout that interval from negative infinity to 1. Now what is f prime of 2? Well, here we probably should go here. 2 minus 1 is 1. 2 minus 3 is negative 1, but if we square the negative 1, we get 1. So 1 times 1 times 12 equals 12. And that's positive. Double check my arithmetic there, but hopefully when you substitute when you substitute 2 for x, you get 12. What if you substitute 4 for x? 4 minus 3 is 1. 1 squared is 1. 4 minus 3 is 1. 3 times 12?
36.
36. So that's positive. Whoa. So you do a few of these, and you see plus minus, plus minus, plus minus. The sign tends to alternate, but then you run into one where it doesn't. We have pluses on both sides of this critical number, and when that happens, it's increasing into it, and it's increasing on the other side of it.
Like a tangent.
So well, there's the graph of kind of no vertical asymptotes here, but it kind of behaves that way, like tangent does, except that what I guess tangent I think has a slope of 1 maybe
At some point.
at 0 rather than this where we're getting a horizontal tangent line. Yes.
Because the fact that 3 isn't a relative extremum will be because x minus 3 is squared, or is that just a coincidence?
It's we could probably find an exception to that rule, but it's something to look for. If we want to put it in the form of a conjecture, what could we say? It's no relative. If f is a polynomial and has a 0 of multiplicity, we need to have even multiplicity. It has a 0 of even multiplicity. Now f prime. F prime. So we're looking at f prime, and f prime has a 0 of even multiplicity. I guess we're referring back to this graph here and seeing where it just touched the x-axis there. Well, if that happens, it's necessarily just since it just touches the x-axis there, it's not going to change sign. So yeah, you could say that. We'd have to really kind of fine-tune that, but I can see it's not a coincidence at all. That's going to happen every time you do this. Yeah.
Something to look for, I guess.
When that multiplicity is even, it'll just touch the graph, and so the first derivative is not changing sign. Then, according to the first derivative test, it's not going to have a relative extremum there. So f has no relative extremum at x equals 3. But f does have a relative extremum. What kind of extremum? Decreasing into it, increasing out of it. F does have a relative minimum, turns out to be an absolute minimum, at x equals 1. Here we go. This problem is maybe the trickiest one we'll have on a test all semester. Something like this. Because the problem asks you a question about the function f, but it doesn't give you a picture of the function f. It gives you a picture of f prime. So here's what I've got to do. I've got to capture this, paste that there, and capture this, and paste it there. And we want to answer a question about the function f, but we don't know what the function f looks like, what its graph looks like. This is the graph of f prime. So judging from the graph of f prime, we want to answer questions about f. Let's see what the questions are. A, identify the critical numbers of f. Now if we do enough with critical numbers, and we're thinking about the graph of f, if we had the graph of f, we would think, oh, that's where it has points at the top of a hill, points at the bottom of a valley, maybe points of non-differentiability, although none of those here because it looks like a nice smooth polynomial. But how does that translate to the graph of f prime? What's going on with the graph of f prime if the graph of f has a point at the top of a hill or the bottom of a valley?
Isn't there such a thing as an antiderivative? Or is that what that is?
Well,
where you can sort of like have an inverse function.
There is, yeah.
Inverse derivative.
We're maybe thinking like that, and we'll do antiderivatives in the not too distant future, within the month.
Isn't there the fact that multiple different equations can come out with the same derivative?
Yeah, the antiderivative will not be unique. That's what we'll see. You can slide the thing up and down, and a lot of different functions will have this as their derivative. But I think we can still answer this question even in spite of the non-uniqueness of the antiderivative. There's some function f out there, a lot of them that have this as its derivative.
Just kind of work backwards with it, like seeing that x to the fourth is 1x to the fourth. So it's the same thing as x to the fifth would be the original function.
So x to the fifth.
But then you would take the 22.
X to the fifth. And then you would have like...
Well, what we'll see, once we answer this question, what we'll see is the antiderivative that I'm thinking of, one of many, is this. Okay, so no peeking, but 1/5 x to the fifth minus 22/3 x cubed minus 12x squared plus 45x plus any constant is going to work here for an antiderivative. But suppose we just have the picture. Suppose, and I guess I've spoiled it, suppose we don't even have this. Scratch it out. I can do that because I know I can erase it later. So, what's happening to the derivative when there are critical points? Critical points are points where the derivative equals what? 0, yes. So on the graph, where does it equal 0? Negative 3, 1, and 5. Okay?
Could you say that if y is going down as it crosses the x, then it would be a relative maximum, and then if it's going up as it crosses the point, it would be a relative minimum?
I think we can say that. Let's see why. If the graph, well, hang on. Wait. If it's pluses here, right? If it's a sine graph for f prime, I want to write pluses where the graph is above the x-axis, because this is f prime. Pluses where the graph that we see is above the x-axis, minuses where it's below the x-axis. So pluses, but more pluses, right? And then minuses, and then pluses. So this is our sine graph for f prime. Next question. Determine whether f has a relative maximum, relative minimum, or neither at each critical number. What's happening at negative 3?
Relative minimum.
Well,
no, it's not going to have anything.
If this were the graph of f, it would be relative minimum, but it's plus plus. So the graph of f is actually increasing going into this and increasing on the other side. So if we're trying to reconstruct the graph of f, we understand it's not unique. There are a lot of different f's that would work here. But something that's, got to be careful with maybe the curvature, do I? So maybe not. Increasing, and then horizontal tangent line, and then increasing on the other side of that. And what's happening? So neither. It does not have a relative minimum or a relative maximum. At 1, what's going on?
Positive to minimum, meaning it's going up and going back down.
Yeah, plus to minus. So going up into it, down, out. So relative maximum. And at x equals 5, going into it, it's decreasing. Coming out of it, it's increasing. So relative minimum. Let me continue with the graph. So I have to be careful because there's something special that happens involving the second derivative. So something like, where's that relative maximum going to occur? At 1?
Maybe drawn a little higher.
Like that, maybe? Maxes out at 1 and then comes back down. And then a minimum at 5, and then increasing the rest of the way. So something sort of like this. It's freehand, so could be off in proportions and various things like that. But to reconstruct the original function, these are some considerations. If we had some additional considerations involving the second derivative and concavity and inflection points and things like that we'll see in 4.4, then we can be a little bit more precise with it. But that's the idea. And what is the C part? Oh, do your best to sketch a rough graph of the function. Okay, we did that. So there it is. Now, the actual one looks like that. So it kind of, compared to what we have, yeah, I think that's fairly decent. Maybe I should have leveled it off a little bit more at -3. I'm not real thrilled about what I did there. Horizontal tangent line right there, so level and then up. But otherwise, seemed like it was okay.
Would it help if we marked where we were having maximums, minimums, or just flatness?
I think so. Yeah, I think if you just maybe draw something like that, and something like that, and something like that, and then indicate, oh, that's got to be the bottom of a valley, that's got to be the top of a hill, that's got to be neither one, and then fill in the rest of the graph based on that. That would be very helpful, I think. And this was what used to be a WebAssign problem. Yeah. That evidently students were struggling with, so I put in the notes. Let's look at 4.3 exercises and see what would be some good ones, some additional ones to practice on in your preparation for the test. Section 4.3. Then we'll see if we can say a little bit about 4.4 before we go today. Is this 4? What is this? It's 4.3. Not so much. Delta intervals where it's increasing or decreasing. If it provides the picture. Okay. Beginning with problem 9. .39 11 15 should be fine because when you take the derivative of that, you lose the x. So you might have the trig function and a constant, but you don't have a mixture of a trig function and a non-constant polynomial. I wonder if 17 is going to be as ugly as the corresponding one in the previous section. I almost think 18 might be nicer than 17. And I think 16. Good grief. Help me out a little bit. I don't like the even numbers. I like 14. That is not useful. Okay, so 13 and 15. Find the critical numbers. Find the open intervals on which the function is increasing, decreasing. Locate all relative extrema. So 25 looks good. 27 for sure. (31 and 35), they're not polynomials, but that's probably a good thing. Get points of non-differentiability and possible location of relative extrema at those critical points. 37 is a nice one. We did a piecewise function. I don't think 43 would be out of bounds. Is there anything? Ooh, 47. 47's nice. 47, I like that. And then they get more extreme. Apply the first derivative test to identify all relative extrema. Use a graphing utility to confirm your results. 59. So we really do have time to work all these problems between now and Wednesday morning, right? Well, we have time to glance at them and say, yeah, I can sort of do that. We'll see.
I have a question though.
61 to 65, yes.
On the
Question.
next test, are you going to go back to having homeworks, or are we?
I think to some extent I will, and on the last couple tests, maybe we're down to the last couple of tests at this point. The last one for sure, maybe the next one next to the last one. I've already got some problems worked out, so it should go back. This is just when I originally did this, it was not something that I could type up very well. It was a lot of handwritten work, and at the time I didn't have a tablet PC, and it was real arduous to do it. Paper, scan, yeah. It would work, but then when I want to edit it, it becomes a nightmare.
That's to draw up the mess.
I still say you give us till Monday.
85. Use the graph of f prime to identify critical numbers. That's just like the problem we finished. 85 is a fantastic one and virtually guaranteed to have something like that on the test. 85. Conceptual stuff there is good. Ooh. That should be plenty. I'm going to say more about this motion along a line in the section entitled A Summary of Curve Sketching. That's going to be my principal examples that I'll use in a summary of curve sketching. So I'll come back and pick up some of those 4.4 examples and make up some 4.3 examples toward the end of the section and make up some of my own when we get there. So you have kind of an idea what to study for the tests.
What question should we do for 3.7?
3.7. Those ones that I listed in the homework actually for last time. If you go there and click on the exam 3 homework, just pick up with those. It was the related rates problems, the relationship between the volume, height, radius, length of a cylinder, and formulas. Formulas. I may very well.
By the way, where are they hyperlinked?
They're hyperlinked to YouTube videos.
Oh.
Have y'all looked at any of the YouTube videos? No. Yeah, if you click on it, yeah, these guys are really good. I forget exactly where they are, this Bull Clio 1, but they have a lot of these in there. It's not a thrill a minute, but it is. They are really clear. They speak slowly, and they support everything they say with graphs. They do a really good job, and a lot of these are linked to those. Some of the first ones, like up here, are linked to Khan Academy. Mr. Khan does a pretty good job most of the time. I think maybe this one was a pretty good one. If you want, I suppose you could just go to the end and look and see what's been written there. But he'll talk you through it. So that's something to consider. Maybe not as nice as having them in printed format, but they'll give you step-by-step instructions. They do a pretty good job. Set it equal to 0. Let's find the critical points. So 3/4 x squared equals 3. X squared equals whatever 4/3 times 3 is. So x squared equals 4. So x equals plus or minus 2. So a couple of relative extrema here. So 2 and negative 2 are values where the first derivative is equal to 0. So let's construct a sine graph for the first derivative, sine graph for f prime, and choose some test numbers that are inside of these intervals. And this particular first derivative should be pretty easy to evaluate. If we square negative 3, or positive 3 for that matter, we get 9. So in either case, 3/4 of 9 is 27/4, and 27/4 minus 12/4, 3 equals 12/4, is a positive number of fourths, 15/4. So the first derivative is positive here, and the first derivative is positive here as well. Get the same value for negative 3 and positive 3 because we just begin by squaring it. They have the same square. If we evaluate the first derivative at 0, f prime of 0 equals negative 3, and that's negative. What do we say, 15/4 for that one? 15/4 for that one. So according to the first derivative test, the pluses indicate it's increasing going into it. The minuses indicate it's decreasing going out of it. So it looks like a relative maximum at negative 2. At positive 2, the minuses indicate that it's decreasing going into it. The pluses indicate that it's increasing going out of it. So relative minimum at positive 2. So it has a relative maximum at each one, and let me refer back and just see exactly how I define relative extremum to see the to see the role of the y coordinate there. Nope, that would have been back 4.1. When we talked about a minimum or maximum, didn't put the word relative in front of it, basically that meant absolute maximum in the interval, absolute minimum in the interval. And it was important to consider the function value, that maximum value or the minimum value, to evaluate the function there. for the existence of a relative minimum, or to say it has a relative minimum or relative maximum, it's not going to be as crucial for you to tell me the value of that relative maximum or the value of the relative minimum. We haven't been doing that in any of these examples, and so I'm not going to do it here or ask you to do it on the test, simply to say it has one there, and not to take the time to substitute the -2 for x in the original function, or the +2 for x in the original function. We do that when looking for an absolute maximum or an absolute minimum, not as crucial for a relative maximum or relative minimum. What's that? Yes, so f has a relative maximum at x equals -2, f has a relative minimum at x equals +2. Okay.